I need one person to confirm if you're hearing. Okay, thank you so much. I want to welcome everyone to my lecture today. Of course, we are having our lecture remotely today because of the ugly incident that happened yesterday. But I'm actually fine. Okay, so I think by Monday I should be fantastic. I should be fine in a way. So I use this opportunity to apologize for not making it to the office hour yesterday. And that was the reason why in today's lecture, I'm only going to spend 50% of the time on the lecture, and I'm also going to spend 50% of the time on office hour today, in case there's anyone who need a clarification, because I value feedbacks a lot. We started logistic regression on Wednesday. The logistic regression, we actually apply that when we're looking at the relationship among variables, and of course, the response variable is categorical. And of course, what I did on Wednesday, I demonstrated the inappropriateness of linear regression, okay, for that kind of situation. So, because, using linear regression, I think I demonstrated that there's going to be violations of normality. There's going to be violation of constant variance, even though those two violations can be fixed. But there's one, fulfillment that cannot be actualized, which is restricting the range of the response variable to 0, 1. And that is the reason why fitting linear regression is basically going to be problematic. There's going to be what I call nonsensical prediction, because the prediction is going to go over the range. And of course, I introduce you to logistical regression. Okay, so today we want to continue from where we stopped. I've walked you through how you can use logistical regression. Okay, I actually show you an R code to do that. We did that in class. But how do we interpret, the coefficients in the logistic regression? And that's exactly what we're going to go over today. We're also going to go over what we call odds ratio. So what is the significance of odds ratio? Okay, you're basically going to learn stuff about that today. Okay, do you remember on Wednesday, I actually walk you through this particular example? In this particular example, we're actually looking at the effect of weight, okay, on the whether satellite is present or not. Of course, the satellite or present or not, that's make that response variable to be categorical. Actually have two levels. Of course, the predator that we have right now is actually continuous. Now, when you take a look at what I have right now, okay, this is the result that we got after feeding logistic regression in R. As you can see, the code right here. And I told you on Wednesday that if you want to feed this code, the difference between this and, the linear regression, the difference is just going to be the GLM. Take a look at that. In the linear regression, we fit LM, which is linear model. But right now, the GLM means generalized linear model. And you also need to specify, you got to state that the family is binomial. You know why? because the probability or distribution of the response variable is binomial. Binomial in the sense that you got two possible outcome, okay, two possible outcome, and you have to specify that whenever you fit in binomial. I mean, whenever you fit in logistical regression. Okay, now another thing that I basically wanted to see now, we've already obtained these results, and take a look at the estimate that we have here. I told you this estimate, they are called log odd estimates. Okay, we call them log odd estimate. Please take notes. Okay, log odd estimate. Now, looking at this estimate now, okay, we're also going to get some other things, and you're also going to learn how to actually interpret that. Now, take a look at what I have here. Here is more or less like I want to focus on the estimate. You can see that, when you do the summary of module.1, okay, when you do that summary, what you basically going to see is going to be a lot of output, right? But if you only want to extract the estimate, the coefficient, you can just do code. You can just write this code, COEF, and it's just going to return this guy. Take a look at that. Okay, now we take a look at this guy. Actually call this the log or the estimate. You get what I mean? Now, if I want to get the odd, now, if I want to go from log odd to the odd, okay, now, what I'm just going to do is to exponentiate this guy. The code now to exponentiate is EXP. Do you see the EXP? What I'm only talking about here is that I want to round my result to 3 decimal. You see the 3 here, right? And that was why we got this result. So what I'm trying to tell you now, there's a difference between this guy and this guy. This is log odd. Why this is odd? Okay, there's a difference between log odd and the odd. This is the odd order or estimate. Okay, now the next thing I actually want to talk about is getting the confidence interval for that. Because this is a single result. This result could be wrong or right. In statistical analysis, to be at the safer side, if I really want to know how reliable is my estimate, I think I need to actually, you know, obtain the confidence interval. The confidence interval will give us an opportunity, to be able to determine how reliable is my estimate. It's more or less like telling us how does, the result that I got from the sample, how does that reflect the general belief in the population? Okay, so that was what you're trying to do here, where you're trying to get a confidence, here you're trying to get a confidence interval, okay, for module.1. Okay, so the confidence, the interval for the odd ratio, don't forget this is ESP. You're getting the confidence interval for this instead of you to be talking about just 0.00. For the intercept, you're going to be talking about between the 0.000 and this guy here, using 95% confidence. Instead of you to be talking about just 1.644, you're going to be saying, okay, that lies between 1.361 and 2.032. Of course, you already know the significance of, getting the confidence interval. Okay. Okay. Now, how do we interpret now? Take it to interpretation now. Okay. So if I want to talk about the interpretation now, how do we interpret the weight, the 0.497? Don't forget, I call this log odd estimate. Log odd estimate. The log odd estimate is the direct result that you got when you fit logistic regression in R. Okay, so if I want to interpret that guy now, That particular guy, I need to look at the sign. Is it positive? Is it negative? This one now is positive. Okay, now if I basically want to interpret that guy, okay, what this guy is trying to say, the probability of a satellite being present increases with increasing weight. How do I know? Let me tell you. When the when the slope is positive, you're going to be talking about that will favor the odd, that will favor the log odd, that will favor the probability. I'm going to say that again. When the slope is positive, okay, that way actually, we it the direction, that very direction will be the same for probability, for log odd, and for the odd. Okay, and that was what I'm trying to say here. I'm applying this now to the fact that the probability of a satellite being present increases with increasing weight. And not only that, if I want to interpret that on the log odd scale, I'm going to say specifically for every 1 centimeter increase in the weight, the log odd increases by 0.497. Let me tell you this. This is not a probability value. This is a log odd value. Okay, this is a log odd value. Okay, but what I'm trying to say is if that increases for the log odd, that will also increase for the odd, and that is also going to increase for the probability. But it is not a probability value. Okay, now if I know that this is a log odd, how do I get the odd ratio? Of course, I exponentiate that. That give me 1.644. Now the question now, if I really want to interpret the 1.644, what am I going to do? I can multiply this guy by 100. If I multiply this guy by 100, okay, 100, whatever I got minus 100 will be 64 point. So this is more or less an increase of 64.4%. So what am I trying to talk about? Well, what do we mean by odd ratio in the first place? If you want to interpret odd ratio, that depends on whether you are having a categorical predator or you are having a continuous predator. But this time around, we're having a continuous predator, which is weight, right? Now, what we're trying to say, what the odd ratio is going to tell us, okay, it's trying to tell you the probability, the order of occurrence of an event. Okay, the occurrence, the odd ratio means the ratio of the probability of occurrence to the probability of no occurrence. So it means that favor the occurrence because the occurrence is going to be in the numerator. You get what I mean? And that is exactly what we mean here. Now, so this is another way we're trying to say a way of starting this just like for every 1 centimeter increase in the weight, there's an increase of 64 0.4% in the heart. Okay, increase. Why do I know there's an increase here? This is going to be over 100. You multiply, and of course I already know from the sign, from the positive sign of the slope, I already know that. Then the confidence interval now can also be calculated, which is what I showed you the other time. Okay, but there's something I wanted to take note. Oh my God, take a look at this guy. It's go from 1.36 to 2.03. If you multiply each of that by 100, if I multiply this guy by 100, okay, that's a 36% gain, right? If you multiply this by 100, that is 103 gain. And that was why I said, take a look at this. For every 1 centimeter increase in weight, there's an increase in the horde, which is going to range from 36% to 103%. I told you, take a look at this guy. 1.36 multiplied by 100, that will be 136. 136 minus 100. 100 is a threshold. Okay, 100 is a threshold. So which is going to be 36 for this guy, and it's going to be 103 for this guy. Take a look at that interpretation now. Okay, so they they may ask a question, what is the estimated probability for satellite being present? Like for instance, if we have a 50%, that the satellite is going to be present. You know what I mean by 50%? 50-50, right? It means the odd ratio in that regard is going to be 1. Because for you to have a 50-50 situation, if the probability of the satellite is going to be present is 50, the probability that it's not going to be present is also going to be 50. They're going to cancel out. You're actually going to have the odd ratio 1. Now, in that situation, if we want to actually get the values of the weed at this particular 50% threshold, I'm going to say this again. If I want to get the value of the weed, what is the value of the weed when we got a 50%, threshold? That is going to be negative the ratio of the beta naught to the beta 1. Of course, we've gotten the beta naught, from the logistic regression output. We got the beta 1, just find the ratio, and they're going to multiply by minus. Don't forget, the beta naught in the, in what we found before was a negative 12. If I want to go back, did you see that? That was a negative 12. Okay, so don't forget, at 50% threshold, it's going to be negative, this divided by that. That is the weight, which is going to be 24.84. So what I'm trying to tell the world now, before I can have a dicey situation, before I can have the probability of the occurrence to be equal to the probability of non-occurrence, what we mean now, the value of the predator have to be this. The value of the predator have to be this. Okay, and in biological, in agriculture or biological discipline, they normally call that 50%. They call it, the effective concentration or the effective dose, or with all the letter dose, or so that's what it means. And let me also tell you this. Do you know at that very 24.84%, centimeter that we calculate, which is the values of the weight, when the probability is actually 50%, that particular value, okay, it means for every 1 centimeter increase in the weight, the probability increases by about this guy. Oh my God, what am I doing here? Take a look at this guy. It's like you are using the probability of occurrence multiplied by probability of non-occurrence, multiplied by the beta 1, okay? And that will give you what I have here, okay? Now, do you know that if you want to, let's say for instance, let's say this is what you're giving. Do you know if you plug in this guy here and here, right? And you plug in the values of beta naught and the beta 1, do you know what this guy is going to give you? This guy should give you 0.5. That is what I mean. Don't forget, this guy is a probability value. Okay, this is having a logistic regression in probability form. I'm going to say that again. This is having logistic regression in probability form. Take a look at that. Is there anybody want to ask question at this junction? Is there anybody who need clarification? Can you all confirm again if you are still hearing me clearly? Can somebody confirm if you're still hearing me clearly? Is
Yeah,
everyone?
we can hear you.
Oh, thank you so much. Thank you for confirming that. Now, I actually want to entertain question in case if anybody need your clarification. Okay. Uh, silence. Oh, let me see my chat. I think it's okay. Do not hide your feelings. Okay. Do not hide your feelings. Ask me question. Okay. So I'm going to go to the next slide. Now, this is what I said the other time. Do you know plugging in that value into the that expression, you're basically going to get 0.5. I think I actually mentioned that. Okay, and if you're giving pi to be 0.5, okay, if I want to find the predator, don't forget I said you're going to do negative times the ratio of beta naught to beta 1. Okay, don't forget that. Okay, now some of you may be wondering, if I want to make a prediction now and I want to use R, okay, if you take a look at this is more or less a prediction. What am I predicting? I already have my model. Okay, I got my model now. This is having logistic regression in probability form. Do you know what I plug in? Okay, this particular, give me 1 second. This particular guy here, don't forget, is a beta null, right? There you go. This is beta null, right? I'm going to call beta null cab. Okay, this particular guy is beta 1. Do you know that? Is beta 1. Do you know that? And this is just X. Okay, it's like we're making a prediction. If I know the values of my X to be that, what I want to do, I want to find the probability. Okay, I show you in class on Monday. That is a probability form of a logistic regression. Take a look at that. We're making prediction now. Okay, so now if I don't want to use the formula, if I don't want to use this formula, and I want to use how am I going to do it? Okay, I'm going to show you. Then not only that, do you know that there are two forms of logistic regression. One in a log odd form, when you have log odd, okay, y cap divided by 1 minus y cap, okay, or if you don't want to use y cap, you can also use a pi. That's no problem. Okay, I've been using pi in this class. So pi, okay, divided by 1 minus pi of x, right? And I write, okay, the beta naught plus the beta 1. Okay, this guy here, okay, is a logistic regression in logit form. This is logit form. Okay, please take notes. Logistic regression in logit form. But what about the one in probability form? Okay, the one in probability form is basically going to be pi of x, okay, equal, and I'm actually going to say that ESP, okay, so please take note in case in the exam, there's a difference between the two. Okay, I'm giving you right now the probability form and the logit form. So that ESP, okay, into beta naught plus the beta 1 x. Take a look at that. This is in probability form. Okay, this is in the probability form, but this guy here is in logit form. Okay, now if you know your beta naught, your beta 1, your x, you can find the probability, right? And if you know your beta naught and beta 1, you can find the log of odd here, right? Now, if I don't want to use formula, now I want to use how. Well, how am I going to do it? And that's what I'm going to show you now. I'm going to show you the code on how to do it. Oh my God, this is going to be super easy. For instance, now, this is for the logit. This is for the probability. Take a look at that. Okay. If you take a look at what I'm trying to tell you now, okay, I'm trying to say, this guy here is the one in a logit form that I have log pi divided by 1 minus pi equal the beta naught plus beta 1 x. Okay, now this guy here is the one in the logit form, but the one here is the one in probability form. Okay, that I actually wrote the other time as ESP. Okay, that I wrote as ESP. Okay, the beta naught plus beta 1 x, okay, all divided by 1 plus ESP, okay, into beta naught plus beta 1 x. If you take a look at what I'm actually doing here, this is the code. For instance, I know my model.1, if I'm giving the weight to be that, okay, what is the difference between the code is just like I'm going to show you now the difference that you have in the code. The difference that you have in the code is just that if you take a look at all of that, the type here equal response. the response for probability. Take a look at that. Take a look at it too. Okay, so that is going to be the, doing it now is going to be so easy, right? That's why we're doing now. Okay, now this is more or less, you know, like if I want to find what is the meaning of the odd ratio, we've been finding. Okay, now do this is what I talk about in the odd ratio, right? But look at the one at the top. Okay, look at this. I say odds. Odds. It means I'm having two odd. This is another odd. But in this odd here, the difference between the odd in the numerator and the odd here is more or less like I move from, my predator increased by one. My predator increased by one. If you take a look at it too, okay, I'm having ratio of odds now. Okay, what I'm trying to say, this guy is an odd. This is another odd, but the odd in the numerator, okay, there's an increase. The predator has increased by one. That's what I mean. Now, using the model that I'm using the data set that we've been using of, talking about that, of course, this is what we have, right? Okay, now I can decide to do this now so that you're going to see, if the weight should increase by one, maybe initially it was 30 and now go to 31. Okay. So we want to look at the odd ratio. Okay. So how do we do that now? Okay. Initially it was 30. It moved to 31. That's an increase, a unit increase, right? Okay. Now, if I want to do that now, take a look at this. Okay. I'm going to do for 30, right? This is for 30 now. Okay. This is for 31. Okay. What am I doing here? What am I calculating? Oh my God, I'm calculating probability. Okay, the probability of the response when x equal to 30, you can see response here, right? You can also see response. Anytime you see response, we mean probability. And don't forget, what is the odd? The odd is the ratio of the probability. But right now, the probability that we are calculating is when the weight increases by one. This is that. Oh, what is this? Am I seeing this guy for the first time? No, I'm not seeing that for the first time. This guy is actually what we found the other time, that we do exponential of beta 1. Do you remember? This guy here is what we got. When we do when we exponentiate beta 1, I'm going to take you back now. This is just what happened behind the scene. I'm going to take you back now. You're going to see what I'm talking about. This guy here. Give me 1 second. Oh my God, it is this guy. You know what we did? We exponentiate, okay? We exponentiate that and actually lead to this. And that was what I was trying to say here too. That, okay, you know what? He said that you get this way or you get it this way. Take a look at that. Okay? Exponentiation of the log or estimate that you got. Take a look at that. And do you know you can calculate the percentage change? Just like what you did in high school, right? The percentage change is 64.4%. You don't. Take a look at that. Oh my God, that is going to be the end of my lecture today. Is there any question before I go into office hour? Because I'm starting my office hour immediately. Is there any question anybody want to ask today before I go into my office hour? Is there any question? If you really understand what I've presented today, I need you to say yes, or you comment yes, or you give me a thumbs up if you really understand what I've presented. Okay. Oh my God, this student really understand what I'm presenting. Good job, everyone. But you know what? If you don't understand, I actually need you to what? Do not hide your feeling. You got to say now. So this is going to be the end of the lecture right now. I want to welcome everyone into my office hours. Okay, in case I know some of you visited my office hour yesterday, and because of the incidents, I was actually not present, and yeah, I'm giving this opportunity now. Between now and the next 20 minutes, I want to listen to, in case you have a question that you actually want to ask, and I'm suspecting maybe the question is about the ongoing assignment. I put it here. I can talk about it. Okay. We want to go first. Who has question? You can go ahead and ask now. This is an office hour now.
I had a
Professor,
question.
I can go first.
Oh, okay. Yeah, go. You can go first.
Okay,
Yeah.
so do you mind if I share my screen?
Okay. Give me 1 second. I'm